So this project is called Physics-Based World Models for Interactive Video Generation. So a bit of background, interactive video generation is a task where a model generates a frame in a video conditioned on past frames of user action, essentially simulating a video game. This is different from video generation models, which generate the entire video at once usually, or they can at least. Whereas interactive video generation is always frame by frame because there's a new action with each frame. So these models are obviously are trained on video games, where the actions of the player affect what the next frame rendered is. Simply tar games, such as games as Doom and Minecraft, have been simulated this way, where we turn a neural network into a game engine. In reinforcement learning literature, this is similar to world models, where an agent learns a world model that predicts the change in state of the world given the agent's actions. However, learning a world model does not entail faithfully representing an image of the world model after changing the state. Like, we don't have to generate an image that a human can look at with each change in state. It could just be some latent embedding vector that only the reinforcement learning agent understands. So what we want to do is a physics-based world model. Usually the world model is trained on state action pairs fed to a neural network with no assumptions regarding how the world actually works. However, we do have assumptions how the world works. The movement of characters in video games is governed by a physics engine, which is usually based on Newtonian equations of motion. So my plan is to build an interactive video generation network that assumes Newtonian equations of motion. Benefits such will be: 1. Compared to the baseline game and gen, our physics-based model will be more accurate. Accuracy defined as MSE between predicted and actual change in location of the user control sprite, and / fewer flops. 2. The user will have the ability to adjust some learned parameters governing the forces that affect the game elements, such as gravity or drift, in order to change the experience of playing the game. Any heavier gravity means you jump less far. So data collection. The data can be collected from running a reinforcement learning agent in a Sonic the Hedgehog level environment, and storing the frame as an image and XY world coordinates of the sprite in each frame. The purpose of this task is not to train the agent particularly well or anything, or do anything novel. We'll just use something out of the box like PPO for policy. The purpose is just to collect a sequence of gameplay images. And as for architecture, we will be splitting this into 2 parts. The world model, which given the state, action, the x, y coordinates, and the velocity is a time t, whereas state is an image embedding of the current frame, action is the action the agent takes inside the frame, jumping, running, moving, etc., and x, y are the coordinates of the agent in the world. We predict x, y at time t plus 1. Then the rendering model, which given past states, the action and x, y coordinates, where past states is a sequence of image embeddings from t minus k to t, action is the same as before, and x and y are the actual predicted coordinates, agent time t plus 1. The rendering model renders the world at time t plus 1, which is a new image. And then we can recalculate the new velocity and find what the new action is, and then pass it to the world model again, and we can repeat indefinitely as long as we have a sequence of actions. So the way the world model works is we assume all the forces on the sprite are a sum of the self force, which is self-directed force from, the sprite has its own momentum and energy, drag, which is directly proportional to the velocity, gravity, which always points downward, and the normal force, which is a function of gravity and the angle of the agent with respect to the horizon. So the world model has trainable parameters G and D representing the acceleration due to gravity and the drag coefficient, as well as model F phi that takes xt, yt, vxt, vyt, action t, and image t as inputs and returns theta, f self y, and f self x, where theta is the orientation of the sprite with respect to the ground, thus affecting the normal force, and f self represents the internal force from the player sprite propelling itself. And the net forces are calculated like so. We don't need to go into that. But then the next part is the rendering model. So the rendering model will just be pretty standard, simple, latent diffusion. And there will be 2 stages. 1, we'll have to fine-tune a pre-trained V8 checkpoint on gameplay images, because this is latent diffusion, so we're not actually working in the image space, we're working in the latent space. And 2, we will fine-tune a UNet plus metadata embedding plus action encoder for noise prediction on gameplay images. The metadata embedding will be used to condition the UNet on the XY coordinates, and the action encoder will take the place of a text encoder, and we'll just do cross attention using the using the action embeddings from the action encoder. The unit checkpoint to base this off of will be a latent consistency model, because those are good at few step generation. So progress so far, we've generated the data. Right now, we have jobs running to train the VAE and to train the world model, and then we need to start training the UNet with action encoder metadata embedding, but that is contingent on finishing the VAE soon. So yeah.